Okay, so draw a mechanism for the following reaction. So we have the overall reaction, right? And now we just need to figure out a mechanism for it, right? Okay, fantastic. So you have this right here, which is a ring. Same ring, right? Okay. We have this methyl coming off it, and right here we have an alcohol, don't we? Okay. That seems okay. Okay, we've seen that. And then we have an acid, don't we? Does everybody see that that's sulfuric acid? Okay. Let me know if you have problems with that, because that is one thing that, by now I hope nobody has problems with that, but it is something that people don't do. They don't memorize those strong acids. Then they have problems with it the entire semester long. Anyways, and then we go and we now have a methyl group here, right? And we have a double bond. Is there a type of mechanism that we can see a lot of that would cause that? It's elimination, right? Yeah, it's some sort of E. But the question here is whether it's an E2 or an E1, right? So there's really only one place to attack here, right? This hydroxide here. What's one of the most, that's not really a good leaving group though, is it? So is there a way of making a hydroxide or a hydroxyl group into a good leaving group? Yeah, protonate it. We have an acid, don't we? Make it H2O plus. So that would make sense for as my first step, right? I need to protonate it, make it a good leaving group, okay? And that means that the electrons on that oxygen need to go into a bond with the hydrogen. The hydrogen electrons have to go onto the SO4, right? Specifically the oxygen it was connected to. Okay, now we don't really need this HSO4 minus anymore, do we? We're done. And in fact, if this had been a, if this had been a water solution, if we had water in here, we could have just easily said H3O plus or something, right? It really didn't matter. But we had this spelled out, so we used it. Fair enough. That gives us our H2O plus. That's a good leaving group. We don't have a good attacker though, do we? So this isn't going to be an attacker attacking to make an elimination. We also know this can't be that because it's not all happening in one go, is it? How do we know it's not happening in one go? Well, it's rearranging. See that? This group would have had to make a double bond if it was happening all in one go, wouldn't it? But it's not. It's happening further down the ring, in the more stable spots for a carbocation, right? Okay. So we now have this good leaving group. It can leave, right? Okay, fair enough. It's going to leave. That's going to allow the electrons in this double bond here to move, or this, why did I say double bond? This overlapping carbon-hydrogen bond, right? So you're making a carbocation here, a positively charged carbon, right? And this can allow the overlapping nearby electrons in the carbon-hydrogen bond next to it to transfer over to here. Essentially, it's moving that hydrogen, right? Okay. So the electrons in the carbon-hydrogen bond go over to here, where we would have gotten a primary carbocation, right? The primary carbocations are very unstable, very high energy. So now instead, we end up with a secondary carbocation, right? Okay. So now we have our water. This can act as a base. We have this very acidic hydrogen here because it's next to a carbocation, exactly. And so the electrons in this hydrogen are going to move into a double bond. And the hydrogen is going to take the electrons on that water, right? Okay. Does anybody have any questions or got lost anywhere there?
So the double bond is
This doesn't form a double bond. This is a hydrogen shift. And oftentimes we had actually seen this written out as 2 steps. But frankly speaking, for this to establish a primary carbocation, it probably would have needed to move the hydrogen electrons in essentially as soon as it established it. Like, it's very unlikely that would actually exist for any length of time, okay? So it's represented here, instead of being represented by a carbocation and then another step where the hydride shift happens, it's represented as it leaving and the hydride shift occurring all as one step, okay? Which is probably actually quite realistic. Making a primary carbocation would have been very high energy. So it's actually probably more likely for the hydride shift to happen as a single step with the leaving of that leaving group. Okay? All right, now, did anybody have any difficulties with this part? Okay. Notice that whenever you do these mechanisms ones, you always want to start with your reactants and then put in your arrows in that first one. And you always want to end with your product, so you can just put that in the bottom somewhere. Okay? And then you always want to fill in. There you go. That making sense? Everybody feel good? Did I lose anybody? No? Okay. Yes, I will do my best to lose you. Wait. That doesn't sound right. Okay.